Hi, today we are talking section 4.2, implicit differentiation. I will go through these notes. I am not going to specifically do any notes. It's just, it's very difficult to do with my mouse on here, but we will be doing some examples in class, and no worries about the examples. So again, implicit differentiation. Implicitly defined functions, what they have are, you can't easily solve for y. So you might have y in multiple spots in your function, and that's what they're talking about. You're going to have to use the chain rule in there. And we'll talk about doing tangent lines and normal lines. So implicitly defined functions is an important problem in calculus, how to find the slope when you can't easily solve for y. So what you want to do is differentiate first with respect to x using your appropriate derivative rules, and then solve for dy dx in terms of x and y together to obtain a formula that calculates the slope at any point on the graph. So this is called differentiation, and we will go through a couple of how this works exactly. So implicitly defined functions, here's one of them. You did it in pre-calculus. So looking at this function would be very difficult to solve this for y, to get y by itself. So we are going to use implicit differentiation to find the derivative of it. So our example here, we're starting with this function, 3y squared plus 2y equals 5x. So we will find the derivative of each piece with respect to x. So on the bottom, we're going to have dx with respect to x. So first thing here, we're going through and we're going to do this derivative. So power rule here, 6y, and then you have to multiply by dy dx because you're doing the outside rule, which is the power rule. The inside is y, you need to multiply by the derivative of y. Then we go through and do this again. So the derivative of 2y is 2 times the derivative of y, which is dy dx. And then this one here, we have 5x, derivative is 5 dx dx, which we don't usually write because we know that just equals 1. So this is what they're going through and doing. So we have 6y, which I said, times the derivative dy dx, plus 2 times dy dx, and then equals 5 dx dx, and we don't write the dx dx, okay? Finally, we need to move all our terms together. So I'm really just going to factor out the dy dx. I am left with 6y plus 2, and then in order to solve for dy dx, I'm dividing both sides by 6y plus 2. And here is my final derivative. Implicit differentiation. So we are going to differentiate both sides. So find the derivative on both sides with respect to x. Collect all of your terms. So move all your dy dx terms to one side, move all the terms without dy dx to the other side, factor out your dy dx, and then solve for it. Lenses, tangents, and normal lines. So we will show lenses do a lot with finding that tangent and the normal line with how we are seeing through the lenses. I'm not going to go through specifically how to do it, but the idea is you're going to have a function that is implicitly defined, and you're going to have to use implicit differentiation to find your tangent and your normal line. So here's an example. This is our lens, and of course there's the tangent line, and here's the normal line when you go straight through the lens. So we will be using examples of this. So find the equations of the tangent and the normal lines to the graph given by this function at the point square root of 2 over 2, square root of 2 over 2. So we need to differentiate implicitly. So the derivative of x to the 4th is 4x cubed plus, now this is a little bit of a problem. We are gonna have to use product rule because I have x squared times y squared. So as we go through here, so they're just saying, I need to find the derivative of this, I need to find the derivative of this, I need to find the derivative of this. So going through the derivative of the second one, I'm doing the first one times the derivative of the second, plus the derivative of the first times the second, and then I'm finding the derivative here, which is minus 2y dy dx. Again, it says treat x squared, y squared as a product. I'm going through and collecting all of my dy dx terms and then solving for dy dx. Okay, so here is the slope of the tangent line. They just reduced by 2 top and bottom. Then what they did is they are putting this value back in. So they put the value in, they ended up with 3. This is the tangent line slope. And if you want the normal line slope, of course, it's the perpendicular slope to it. So it'd be negative 1/3, and then write your equation. Again, this is usually where I stop. And that is perfectly okay with me. Oh, that wasn't very straight. Example of higher order derivatives. So these are kind of fun. You have to do some simplifying. So there's a lot of algebra too in it. I think that's probably why I think it's so fun. But we need to differentiate with respect to x. So we have 2x, 2 plus 2y dy dx. So I move the 2x over and divide by 2y, simplify. I get negative x over y. So here is a circle. The derivative is this, and it's the same for every circle. So you're going to get that same value. Then you're differentiating again, because this is what it's asking for. Second derivative, not just the first. So I'm going to keep going. So I need to do quotient rule. So low d high minus high d low all over low squared. And when you get that, notice that I have a dy dx in here. When I have a dy dx in there, I'm going to take what my dy dx was equal to, fill it back in, and simplify. So that's what they did. They did a bunch of simplifying, and there's like 2-3 steps in here, and then they got to this step. They didn't show the other work, but that's basically what we are going to have to do. Another power rule, again, I don't think that this is much different than what we had seen before. You take your exponent, you drop it down, subtract 1 from the exponent. And that is it for this section. We will be doing quite a few examples in class.